Oh, okay. So welcome to the third lesson of one and two variable analysis. So we're looking at graphical displays. So we're going to revisit the histogram again today, and we're looking at like how to read the histogram, and we're going to introduce a new graph called the box plot. So this is a great quote from Emily Oster. She's an economist and works at the University of Chicago. The greatest moments are those when you see the result pop up in a graph or in your statistical analysis. That moment you realize you know something no one else does, and you get the pleasure of thinking about how to tell them. So if you got something from your one variable or from your graphs in the last unit, something some interesting conclusion, then you saw this, and so now you get to like kind of write this report to tell people. Um, so warm up. I'm gonna go through this presentation pretty quickly because there's a lot of things here. So if you just need to slow it down and repeat it, then you can pause it and rewind. So question. This is the healthcare data for the year 2000 that we used in the past, and so it is like the percentage of people that ranked healthcare good or excellent. So the question is like, what do you notice or wonder about the one variable stats we've talked about so far? So we've talked about mean, median, modal interval, standard deviation, IQR, and range. And the IQR has the Q1 and Q3. So this is actually a new graph. So I just invite you to pause it and take some time to think about, like, do we know any of those measures? What might those measures be from these numbers? You can see the data here. Remember that like this gives you, there's one point between 0.7 and 0.73. 2 points between 0.88 and 0.9, and then nothing above that. So learning goal today, so we're still looking at the big idea of just distilling information from data and to make informed decisions, manage risk, just to see what the data is telling us so it can help in the long run to make decisions. We're going to be looking at displaying data with histograms and box plots. So histograms are something we've seen already, but box plots are something new. And then comparing two related one variable data sets. That'll be the goal of the first half of the unit, is to compare two related one variable data sets. So we're looking at displaying histograms with technology, which is something we've already done, displaying box plots with technology, and then making conclusions about your measures of central tendency, measures of spread, and comparing data. So histograms, like we just use technology to generate histograms. And I think I mentioned this before, but officially, Google Sheets does the histogram automatically, but you have to actually alter the bucket size under customization. So the question is like, is the interval size nice? Can you read it? Did they pick one that would default kind of nicely? So you could say, yeah, there's that much data between 0.83 and 0.85. And then do you have enough intervals represented? If you have a lack of data, you're not going to really get a nice histogram. But if you have enough data, you should be able to see a nice shape from the histogram. And so a good rule of thumb is to have between 5 and 10 intervals. You don't want to have too few because then there would be too much data in each interval, and you wouldn't get a really good shape. You can imagine like every data might be in one interval, but you don't want it too many because then there might only be one piece of data in each interval. So between 5 and 10 intervals, just so that you can 5 to 10 bars as well on the histogram. The distribution, there are four specific shapes of distribution that we're going to look at. The first one's uniform. So this is bus wait times. This is artificially generated data just from a random number. But the idea here is that like if you're waiting for the bus and you don't know when the bus is coming, and no one knows when the bus is coming, if it just came at random times, but every 15 minutes, when you get there, you can also say that like the decisions you make in the morning or going up to the bus aren't impacted by, which is a reasonable expectation because it comes so often that you just get there when you get there and you catch the next bus. So that means that anybody would be just as likely to have to wait 0 to 1 minutes as they would be waiting 14 to 15. So roughly all the bars are the same height, Really no clear difference. That's uniform distribution. Each interval has an equal chance of being represented, so we've got like this kind of random, and every interval can randomly come up. And you can say that the data is random throughout, or the data is steadily increasing or decreasing if you're looking at the variable over time. Mound shape. So this data was actually artificially generated as well, but it was based on some numbers that were given about coal plants from a Google search, just about CO2 release of coal plants in the U.S. But the number in each category, I actually assumed it was normally distributed, but it does kind of match up with the number of coal plants in the U.S. and the average certainly works as well. So the second type of distribution is mound shape. The most occurring interval is in the middle. And the median is roughly the same as the mean. Like that's what we actually know if it's mound shape. The modal interval is also like right in the middle as well. So you can tell the modal interval is between 3.5 and 3.65 million. And then it is just as likely that the data in a high interval as in a low interval. So these guys that come up here between 5 and 5.15, like they get kind of balanced out by these ones that are below as well. This is our focus of Unit 6. If you're wondering where the source is, I'll put it in the slideshow that would accompany this video. The bimodal shape is when you have, and so this is the Blue Jays batting averages in 2016. So you actually have two peaks. They don't necessarily have to be the same height, but they are like these two kind of peaks. So it's this U shape that it makes. And what it tells you is that there's potentially two groups of people in the data. And you might have to like separate the data or take out one of the groups to really analyze it a bit better. In the graph shown, they're actually showing all the Blue Jays that had an at-bat in 2016. So if you go to the Blue Jays website, they'll give you batting averages, but they'll give you everybody. And so there's 8 players that like maybe are at 0 because they just didn't get a hit because they only got like 1 or 2 at-bats. So pitchers potentially only get to bat once or twice in a season for the Blue Jays because they only pitch or hit when in certain games. And then also just guys that get called up, like young guys that just get called up for a game and then get sent back down. A skewed shape. So this is this again. I can put the source in the website or in the slideshow, but this is from Stats Canada. It's the violent crimes from 1962 to 2016. What this isn't is a time series. So this does not say that crime is going up. It doesn't say that at all. It's just saying that there were the most number of years between 950 and I think 150 more, so 1100 violent crimes. So there are the most years in that category. For comparison, like this is kind of gives you an idea for comparison. It's really only useful if you compared it against another country of similar size, or we put these as percentages of the population over the same period, 62 to 2016. So skewed data is pulled to one side or another, and so it actually peaks on one of the sides. And it doesn't necessarily have to peak on the far side. It could peak like just on the second last one. The type of skew that we call it kind of says like what way the average is being pulled. So this is actually, so positive right skewed would mean the average is being pulled to the right. This is actually negative left skewed. Because there's some numbers that are way lower than where the median is, which the median would be somewhere in here, the middle number, because there's so many right here. The average, because there's these points that are just being pulled that are just way lower than the median, the average is actually going to be lower than the median. That's not always the case, but generally in a skewed data, what the skew means is the average is being pulled to the left. So this is left skew. The modal interval may also be on the median or to the right of the median. So the median could be in here or in here. We'd have to look closer at the data, but the average is being pulled to the left. So what's really important there is the direction of the skew is the direction which the mean is pulled.